Hello everybody. In this video we are going to look at the solutions to the honors electromagnetic induction homework problems 11 through 15, and these problems will all deal with transformers. Let's take a look at problem 11. A transformer has 320 turns in the primary coil and 120 turns in the secondary coil. What kind of transformer is this, and by what factor does it change the voltage? By what factor does it change the current? So I am given the number of turns in the primary coil at 320. I am given the number of turns in the secondary coil, 120. And I know because there are fewer turns in the secondary coil than in the primary coil that this is going to be a step down transformer. We are going to be stepping down the voltage of the transformer. So we're going to have less voltage in the secondary coil as there is in the primary coil. In other words, there's going to be less voltage going out of the transformer than there is going into the transformer. So I want to know the change in the voltage by the factor of the change in the voltage as well as the change in the current. For the change in the voltage, I'm going to use my transformer equation with voltage in it. And note in this equation that the secondary value for the voltage is in my numerator, and the secondary value for the number of turns is also in the numerator. And then in the denominator, we have the primary values for each one. So there's a direct proportionality to this. So the change in the voltage is going to equal my secondary voltage divided by my primary voltage. It's going to be a ratio, and that's equal to the secondary number of coils divided by the primary number of coils. So 120 turns divided by 320 turns is going to give me a ratio of 0.375 or 0.38. For the current, I'm going to do the same thing, but with the current, notice that for current, I have the secondary value, or the secondary current in the numerator, and I have the primary number of coils in the numerator. And it is reversed for the denominator as well. In the denominator, I have the primary current and the secondary number of coils. So there is an inverse proportionality to current. So the change in the current, again, is my secondary current divided by my primary current. And that's going to equal my primary number of coils divided by the secondary number of coils, the reverse of what we did for the voltage. So 320 turns divided by 120 turns equals 2.67, or a ratio of 2.7. And because these are ratios, there are no units for that. And if you notice in this, my units will cancel out in each of these. So I am dimensionless when I'm talking about a ratio. Problem 12 asks, a step-up transformer increases 25 volts to 120 volts. What is the current in the secondary coil as compared to the primary coil? We're given the primary voltage of 25 volts, the secondary voltage of 120 volts. We're told it's a step-up transformer and my output voltage is greater than my input voltage, so that makes sense. And we're being asked to find the comparison between the current in the secondary coil and the primary coil. So again, we're looking for a ratio. I know that the change in the current is going to be equal to my ratio of the input voltage and the secondary voltage. And I know that Vs over Vp equals Ns over Np. And I also know that the relationship between my input and output current and the number of coils. So I know that Is over Ip equals Np over Ns. And because I have Ns over Np related to voltage and Np over Ns related to current, notice that those are the inverse of each other. So now I can say that the current is related to the voltage, but I also have to flip that over or take the inverse of that because I have an inverse relationship in the number of coils from voltage to current. And when I do that, I'm going to end up with Vs over Vp equals Ip over Is. So I'm essentially just taking this and swapping it for that. But when I do, I need to take the inverse of it or flip it over because I have the inverse right here. And I'm ending up looking at the comparison between my secondary current compared to my primary current. So I need to flip both of these ratios over. And when I do that, I have Is over Ip is going to equal Vp over Vs. And my primary voltage is 25 volts divided by my secondary voltage of 120 volts is going to give me a ratio of 0.21. Problem 13. Neon signs require 12 kilovolts for their operation. To operate from a 240 volt line, what must be the ratio of secondary to primary turns of the transformer? What would the voltage output be if the transformer were connected backward? We're given the secondary voltage of 12 kilovolts, which equals 12,000 volts, my primary voltage of 240 volts, and we are looking for the ratio of secondary turns to primary turns in the transformer. And then the second thing that we need to find is the secondary voltage if the transformer is connected backward. So to find the ratio of number of turns in the transformer, if we're looking at the secondary number of turns compared to the primary number of turns, I know my ratio is going to be NS over NP, and that is going to equal Vs over Vp. So the secondary voltage of 12,000 volts divided by the primary voltage of 240 volts is going to give me a ratio of 50, or the two significant figures 5.0 times 10 to the first. What that means is that however many coils I have on the primary side of the transformer, I need to have 50 times that number of coils on the secondary side. So if I have 10 coils on the primary side, I need to have 500 coils on the, what did I say, 50 or did I say 10? I can't remember. Let's try that over. If I have 10 coils on the primary side, I need to have 500 coils on the secondary side. If I have 20 coils on the primary side, I need 1,000 coils on the secondary side. If I wire it in reverse, that now means that I am going to be decreasing my voltage by a factor of 50. So whereas I had a ratio of 50 in my primary or in the first part, now I'm going to have the inverse of that in the secondary voltage if I wire it backwards. So instead of increasing my voltage by a factor of 50, I am going to be decreasing my voltage by a factor of 50. So 240 volts divided by 50 is going to give me a voltage of 4.8 volts. Problem 14. A model train transformer plugs into a 120 volt AC and draws 0.35 amps while supplying 7.5 amps to the train. So we're given the primary voltage of 120 volts. We're given the primary current of 0.35 amps, and we're given the secondary current of 7.5 amps. We want to know what voltage is present across the tracks. So we want to solve for the secondary voltage. I know the relationship between the voltage and the number of turns, Vs over Vp equals Ns over Np. And I know the relationship between the current and the number of turns, Is over Ip equals Np over Ns. So I have Ns over Np here, and I have Np over Ns with the current. Because these are the same, it's just the inverse of each other, I can now take Is over Ip and substitute it in for the Ns over Np in my first equation with the voltage. But because I am taking the inverse here, when I flip it here, when I substitute it, I have to take the inverse of this. And when I do that, I'm going to end up with Vs over Vp equals Ip over Is. Note that this guy and this guy are the inverse of each other. And when I solve this, I'm just going to make a couple of erasures here just so I'm not too confused here. When I solve this guy, when I solve this guy for the secondary voltage, or Vs, I'm going to end up with Vs equals Vp times Ip over Is. And that might seem a little bit confusing, but remember, you can just cross multiply here, because it is just a ratio, and then solve for Vs. So I have Vp times Ip in my numerator, and then I divide both sides by Is, and that's where I end up with my final version of the formula, Vs equals Vp times Ip divided by Is. I plug my known values into there, and I'm going to have a secondary voltage of 5.6 volts. The second thing that they want us to find or ask us is this a step up or step down transformer? And because my secondary voltage is less than my primary voltage, right, my secondary voltage is 5.6 volts, my primary voltage is 120 volts. Because 5.6 is less than 120, this is a step down transformer. Problem 15. A transformer has 330 primary turns and 1340 secondary turns. The input voltage is 120 volts and the output current is 15.0 amps. What are the output voltage and input current? I'm given the number of turns on the primary coil is 330 turns. The number of turns in the secondary coil is 1,340 turns. My primary voltage is 120 volts. My secondary current is 15.0 amps. I'm being asked to find the secondary voltage, and I'm also being asked to find the primary current. To find the secondary voltage, I know I need to use Vs over Vp equals Ns over Np. I'm given 3 of these variables, so I just need to find the 4th. I'm given both the primary and the secondary number of turns, and I am given the primary voltage, and I'm just being asked to find the secondary voltage. So solving this for the secondary voltage, again, I can cross multiply, and when I do that to solve for the secondary voltage, I'm going to get the secondary voltage equals the primary voltage times the secondary number of turns divided by the primary number of turns. I plug my known values into that equation, and I am going to get a secondary voltage of 487 volts or 490 volts to 2 significant figures. Going to follow the same procedure for the primary current. In this case, I am going to use Is over Ip equals Np over Ns. Once again, I am given the primary and the secondary number of coils, and I am given the secondary number, the secondary current or the output current, and I'm being asked to find the primary current. Once again, I can cross multiply, and when I do that, I am going to solve for the primary current, and I'm going to have the primary current is equal to the secondary current times the secondary number of turns divided by the primary number of turns. Plugging my known values into that equation will give me a primary current of 60.9 amps or 61 amps, rounded to 2 significant figures.